Welcome to the very last video lecture for the MPP Calculus course. Your other assignment for class this week is to complete the practice exam and score it yourself. All right, so this will be a quick lecture. It's just covering the types of integrals that you're likely to see in your Harris classes. I suspect some of you have already seen these. I know that they come up in some of the more advanced classes like cost benefit. So I just wanted to cover them very quickly so that you had a basis to come back to when you do run into them in your classes. So the question is, what can economists learn by taking an integral? Conceptually, if you have the graph of a function like y equals x squared, when you take the integral, in a physical sense, what you're calculating is the area between that graph and the x-axis. So in this case, this would be the integral, the shaded blue area would be the integral from x equals 0 to x equals 8 of the function x squared. If you have two graphs, you can also find the area between those two graphs. So for example, you can imagine calculating something like producer or consumer surplus using this technique. So let's look at this notation that we have for integration. The first thing you see is this curly Q. That's simply the symbol that says take the integral. The letter at the bottom is the lower limit. Typically that'll be the smallest number, although not always. The number on the top is the upper limit of integration. So on that first integral we saw before, on that first graph, the lower limit would have been 0, the upper limit would have been 8. Then you write whatever function you're trying to take the integral of. We call that the integrand, although you probably won't ever hear that terminology again. And then this dx at the very end is basically a way of providing a close bracket. So you can think of the integration symbol as the beginning of the integral, and the dx or dy or dq, whatever it is, as the end of the integral. It's signaling not just the end of the integral, but it's also telling you if you have multiple variables with respect to what variable you are taking the integral. So just like when we were doing derivatives, you had d dx or d dy, and that signaled to you with respect to what variable you were supposed to be taking the derivative. Here, the dx at the end is simply saying you need to be taking the integral with respect to the variable x. For the sake of this class, you're only ever going to see single variable problems, but if you ever do end up seeing integrals in multiple variables, that's what it is signaling. Okay, so I said that the very first thing we might do is we might be interested in taking the area of a graph between a graph and the x-axis for the values x equals a to x equals b. So in terms of the notation we just saw, it would be written exactly the way the previous slide was. On the other hand, if you're interested in finding the area between the graphs of f of x and f of g, what you're going to do is take the integral of the first function minus the second function. So just to give you a sense of why that's the case, let's look at that other graph that we saw. So here you can think about the first function, taking the integral of just f of x would give you the area between just x squared would give you the area between the blue line on the bottom and the x-axis. While taking the integral of 10 minus x squared would give you the area from that curve all the way to the x-axis. So if you're interested in the area between the two graphs, you would take the integral of the first minus the integral of the second, so that you're subtracting off the lower area between this blue line and the x-axis. And that sort of setup should cover most of the types of integrals you're ever likely to see in any Harris class. So the next step is to ask, how do you calculate an integral? For this, you use what's called the fundamental theorem of calculus, or the fundamental theorem of integral calculus. And the basic idea is that the integral is the inverse function of the derivative. So if you pause for a second, just in your head, think about taking a multiplication, so 5 times 6. You know in your head that the way that you undo multiplying by 5 is by dividing by 5, because division is the inverse function of multiplication. The same concept applies here. If you want to take an integral, what you need to ask yourself is, what function would produce this if I took its derivative? So we call this the antiderivative. So we might ask, if your function f of x that you're trying to take the integral of is 5, well, what function has the derivative 5? The answer is 5x. Now, I want you to notice that here, although I'm going to stop doing it pretty quickly, I'm adding a constant c, and there's a reason for that. The derivative of 5x is 5, but the derivative of 5x plus 3 is also 5, and the derivative of 5x minus 20 is also 5. So if you're just doing this without any particular interval in mind, you would be doing what's called a indefinite rather than a definite integral. And you'd need to make it specific and say, well, I could have a constant here, but since the derivative of a constant is 0, I have no idea what that constant could be. In a minute, we'll be taking definite integrals, and what'll happen is those c's will cancel one another out, so that if you're looking at a particular area, you don't need to worry about this c because it would cancel out. Okay, so let's look at another antiderivative. If you ask what function would have the derivative 4x? Well, so think it through. The x would need to be x squared, right? Because for the power rule, it would produce an x squared. An x squared would produce an x. However, the derivative of x squared is 2x. So I also need to unwrap that 2 a little bit. So the way that I would find that is I would say, well, I need to divide by my new power and add 1 to the power on the function, on the variable. So this is the reverse of the power rule for derivatives. The power rule for derivatives was subtract 1 from the power and multiply the coefficient by the original power. Here what you do is you add 1 to the power and you divide the coefficient by the new power. So here the new power is 2. We have x squared. So I need to divide my coefficient 4 by 2. And so I get that the antiderivative of 4x is 2x squared plus that constant term that we won't worry about much past this instant. The nice thing about integrals is that just like derivatives, addition and subtraction are additive. So what I mean by that is when I take the derivative of a polynomial, I don't need to worry about how many terms I have. I just take each of the separate terms and take their derivatives individually. Because derivation works that way, so does integration. So here where I have a polynomial x to the 4th plus 2x, I can separately ask what function would produce the derivative x to the 4th and what function would produce the derivative 2x, and just treat them completely separately. So for the first one, I'm going to use that reverse power rule. I'm going to say, well, x to the 4th, I need to add 1 to the power. I would get x to the 5th. But if I were taking a derivative, I would be bringing that 5 down, so I need to divide the coefficient by 5. So the first term would become 1/5 x to the 5th. And then the second term, you might immediately recognize that as just the derivative of x squared. If you didn't, you would think it through. You would add 1 to the power to get x squared, and then you would divide the coefficient 2 by the new power, which is 2, to get 1. So the antiderivative here is x to the 5th times 1/5 plus x squared plus a constant that when we take integrals will end up going away. So as long as you have a continuous function on the interval that you're interested in, the way that we find the actual integral of that function is by taking the antiderivative and then substituting in the limits of integration. Formally, this is how it's written, and I want you to just take a minute to look at the notation for each of these 3 chunks. Clearly, the first notation is what we've seen before. Once I take the antiderivative, there are really sort of 3 steps in this process. I take the antiderivative. In the middle, this notation is saying, well, this is the antiderivative, but I need to evaluate it at the limits b and a. And then the last step is to plug in those limits and take the value of your antiderivative at the upper limit b and subtract from it the value of your antiderivative at that lower limit a. And that will give you the value of the definite integral, which will be the area between the function, the x-axis, and the 2 lines x equals a and x equals b. So just to use the same examples that we were looking at before, if I have 4x, its antiderivative is going to be 2x squared. I need to evaluate it at the 2 limits of integration, so I would have 2b squared minus 2a squared. If I want to get even more concrete, let's imagine that I have specific limits in mind. Let's say I want to evaluate the integral of the function for x between a and b, but let's say that a is equal to 3 and b is equal to 5. So that would be the integral from 3 to 5 of 4x. The first step is basically the same. And then at the end, what I need to do is plug 5 in. So I have 2 times 5 squared minus, plugging 3 in, 2 times 3 squared to get 32. Okay. I'm going to do the same example that I had before. If I take the integral of just the number 5, I want to evaluate it at the 2 limits. The antiderivative is 5x, so I'm going to evaluate it at b minus evaluating it at a. If I take the limits of integration to be 3 and 5 again, I'm going to plug 5 in for the first limit. I get 5 times 5 is 25. And subtract from that 3 plugged into the antiderivative, so that I get 3 times 5 is 15, so that I get 25 minus 15 equals 10. Now this is an integral that's easy enough that you could actually just figure it out drawing a picture. So the line that we're trying to integrate is y equals 5. We're looking for the area between y equals 5 and y equals 0. So that's going to be, the vertical height there will be 5. And then between the line x equals 3 and x equals 5. Well, the horizontal distance there would be 2. You're looking at the area of a rectangle here, whose height is 5 and whose horizontal width is 2. And so the area of that rectangle would be 10. You can try this on a few simple functions. Look at the integrals of straight lines, look at the integrals of horizontal lines. You can't do integrals of vertical lines clearly because the limits of integration wouldn't make any sense. But try it out on your own, just on a few functions that you create for yourself, and see if you can use the integral to get the same answer that you would get as if it's a horizontal line, taking the area of a rectangle. If it's a straight line that's not horizontal, it's going to be the area of a triangle plus the area of a rectangle. All right, so let's do one last example. Let's go with the slightly more difficult x to the fourth plus 2x that we saw before. This is probably a good moment to pause the video and see if you can do this integral on your own. All right, so we take the antiderivative. We get 1/5 x to the fifth plus x squared plus c. And you can probably understand a little more clearly why that c goes away now. When you take the upper limit, you would have a positive c, and when you take the lower limit, you would have a negative c, and those two c's would cancel out as a result. All right, so if you're taking the integral from a to b of x to the fourth plus 2x, you are going to evaluate it at the upper limit minus evaluate it at the lower limit. So if you have just generic limits, b and a, it would be b to the fifth over 5 plus b squared minus a to the fifth over 5 minus a squared. On your own right now, why don't you go ahead and try doing this with concrete limits. Let's take it from a equals 1 to b equals 2. So the integral from 1 to 2 of x to the fourth plus 2x. All right, so I chose those limits at least partially because the math gets hairy otherwise. So we plug in 2 here, we get 32/5 plus 4. We plug in 1, we get minus 1/5 minus 1, and that comes out to be 9 1/5. So you've already basically seen most of the important properties of integrals, but I want to just formally write them down for you. The first is that if you take an integral between a point and itself, the value of that integral is going to be 0. The second property makes sense if you think about plugging in the two limits. If you simply flipped the limits and you were looking at the integral from b to a instead of from a to b, the answer is just going to be the negative value of what you got taking the integral from a to b. If you have a constant multiplied by every term in the function, you can factor that all the way out of the integral. That only works for constants, doesn't work for variables, but constants can be pulled all the way out. If you have two functions added together or subtracted together, you can take the integrals separately. You don't need to, there's no difference. That's the way that most people usually do it. Finally, if you have a function from that you're evaluating from a to b and you want to break the integral into sections, that's just fine. The integral, so imagine that you have a point c that's somewhere between a and b. You can take the integral from a to c and add the integral from c to b, and the answer will be the same. And if you think about that in terms of areas, that makes a lot of sense, that you just add two areas together, you get the area of a larger, you get a larger area. So those are all of the properties. In practice, the ones that you use most frequently are 3 and 4 here, that you can pull out the constant and that you can split addition and subtraction up. Just to give you a little more economics grounding on times you might see it, anytime that you have a function that is a rate, the area under the function is going to be the total accumulation at that rate over the period represented by your interval from a to b. So for example, if you think about the graph of the marginal cost, you're graphing the marginal cost per unit And then if you're looking at the integral from A to B, that integral is telling you what is the cost of increasing production from A units to B units. So it's the total cost rather than the per unit marginal cost. If you're looking at a productivity graph, so for example, we usually think that workers become more productive for the first little period of work and then gradually over the course of the day become less productive, although it could be a more complicated function than that. If you have a graph of units per hour or tasks per hour completed over time, the integral is going to tell you how much total work is done between hours A and B. If you have a graph of sales per day, same basic idea, the integral from A to B will tell you the total sales completed between day A and day B. So we'll just do one straightforward example of this. I want you to imagine that you have an employee whose work function over the course of a day looks like this. You see a ramp up time, and then you see that's represented by the 4T. You have a standard number, a base number of units per hour of 20, and then you have a ramp down function that over the course of the day the person becomes less productive, represented by the minus 3T squared. So that's the number of hourly units the employee might produce over the course of a normal shift. And you can imagine a shift starting at 8 a.m. and you might be interested in knowing how many units the worker produces between 9 a.m. and noon. Go ahead right now, see if you can write down that integral for yourself. All right, so you should have something that looks like this. You're looking at the units produced between 1 hour into the shift and 4 hours into the shift. Go ahead and try and take the antiderivative of that. Pause the video. And go ahead and try and evaluate that at the limits of integration if you haven't already done so. All right, so what you should have gotten is negative t cubed plus 2t squared plus 20t. And for definite integrals, never worry about that constant of integration. You know it's always going to cancel out. So you're going to take this function. You got the t cubed by dividing the 3 coefficient by the new power 3. You got the 2 coefficient by dividing the original coefficient by the new power, so 4 divided by 2. And if you have a constant, you just add the variable, so you have 20t. So you go ahead and evaluate at the top limit, minus evaluating at the bottom limit. You get minus 4 cubed plus 2 times 4 squared is 16, plus 20 times 4. Minus, and I just use the parentheses so that I don't have to worry about distributing the minus sign yet. Negative 1 squared is negative 1. Plus 2 times 1 squared is 2, plus 20 times 1 is 20. And if you calculate that out, you should get 27 units. All right, so that was a really basic introduction to integration, but that covers all of the kinds of integration you're likely to see in your Harris classes. So I wanted to be sure that this class had fully exposed you to that. For the sake of testing, I am only ever going to ask you to take the integral of a polynomial. Okay, so there are lots of techniques for taking integrals of more complex functions. I will never ask you to do that. You will only from me see the integrals for polynomials. So with that in mind, happy studying, good luck on the practice exam, and I will see you on Monday.